Hello everyone, I am student of SVC Bangalore. My name is A. Purna Seshisian, USN 1VE22 IS001, Department of Information Science and Engineering. Subject is Discrete Mathematics. Today, the main topic of our presentation is definitions and example of particular group, that is Klein 4 group. So, introduction to Klein 4 group. The Klein 4 group, denoted as V or K4, is a specific type of group in mathematics. It is a non-abelian group with 4 elements. Basically, what is an abelian group is? A group consists of 4 properties. An abelian group will have 4 properties as well as one specific property called commutative property. So basically, our Klein 4 group is not an abelian group. It does not have commutative property. So the group is named after Felix Klein, a German mathematician. Elements of Klein 4 group. The Klein 4 group consists of 4 elements E, A, B, C, and E is an identity element, which returns the same element when combined with any other element. The other 3 elements A, B, C are all of order 2. Multiplication table of Klein 4 group. The multiplication table for the Klein 4 group is as follows. The row elements are E, A, B, C. The column elements are E, A, B, C. When we multiply the first row element with the first column element, we will get a particular value, and that's our table, and that forms a table. Properties of Klein 4 group. The Klein 4 group is a non-abelian group, meaning that the order of multiplication matters. It is also a group where every element is its own inverse. The group is isomorphic to the direct product of Z2 and Z2, denoted as Z2 cross Z2. So basically, our Klein 4 group is of A comma B, where A square equal to B square equal to AB whole square, and all these 3 will be equal to E, that is our identity element. Cayley graph of Klein 4 group. The Cayley graph of the Klein 4 group is a square with each vertex representing an element. The edges of the graph correspond to the group operation between elements. The graph illustrates the relationships between the elements in the group. This is basically Cayley graph of Klein 4 group. Subgroups of Klein 4 group. The Klein 4 group has 3 non-trivial subgroups, that is EA, which is IE, where E is an identity element, and EB and EC. Each of these subgroups is isomorphic to Z2, the cyclic group of order 2. The Klein 4 group is its own normalizer as well as its subgroups are normal. Applications of Klein 4 group. The Klein 4 group has applications in cryptography, particularly in the design of encryption algorithms. It is used in physics to represent symmetries in crystal structures. The group also appears in combinatorial designs and coding theory. Example 1, that is symmetry group. Consider a square with 4 rotations: the identity, the 90-degree rotation, a 180-degree rotation, and a 270-degree rotation. The group of these rotations is isomorphic to the Klein 4 group. Each element corresponds to a different rotation of the square. This is basically our example 1, which shows symmetry group. Example 2 is vectors in 2D space. In the right side, you can see the diagram of a vector in 2D space. Basically, in 2D space, consider the vectors 1, 0 and 0, 1 as basis vectors. The Klein 4 group can be used to represent the symmetries of these vectors under reflections and rotations. The group operations correspond to transformations of the vectors. Our example 3 is quadratic fields. In algebra, the Galois group of quadratic field extension can be isomorphic to the Klein 4 group. The group represents the symmetries of the roots of a quadratic polynomial over the field. Understanding this group helps in studying fields, extensions, and polynomial roots. Okay, Klein 4 group. So as I told, Klein 4 group is nothing but A square equal to B square equal to AB whole square equal to E. That is the identity element. So now let's solve few problems on Klein 4 group. So now solve A dot B dot A dot B. So basically our question is A dot B dot A dot B. Now by using commutative property, we can write this as A dot A dot b dot b, where a dot a is nothing but a square, b dot b is nothing but b square. As I told, a square equal to e and b square equal to e. So this will become e dot e, that is nothing but e, our identity element. Now, let's verify product rule. AB, AB. So basically, the product rule is they have given AB dot AB. This can be written as AB whole square. As I told earlier, AB whole square equal to is our identity element. Now, let's verify our binary operation. See, what basically our binary operation tells. Whenever we have a square and b square and ab whole square, that's nothing but e. So our binary operation question is something like this: a dot b dot a. So this whole thing can be written as like this, whereas a dot a we can remove this brackets and we can write a dot a by using associative property. A dot a dot b dot a by associative property. So where a dot a is nothing but a square dot b dot a. We know that a square is nothing but a Klein group that will be told as e. So e dot b dot a. So this is basically our binary operation sum. Whatever the question might be, we can solve it with the help of this basic rule: a square equal to b square equal to ab whole square that equal to e. This is basically an identity element, and this is our definition of Klein group. So therefore, the Klein group is a fundamental concept in group theory with diverse applications. It exhibits non-trivial properties such as non-abelianness and self-normalizing subgroups. Understanding this group enhances mathematical reasoning and problem-solving skills. This is all about definition and explanation of Klein group. Thank you.